Dear students, in this video we will see the fundamentals of Cayley-Hamilton theorem. That is, what are the basic concepts that are required to prove Cayley-Hamilton theorem. I am not giving proof of the Cayley-Hamilton theorem. So what is the statement of Cayley-Hamilton theorem here? Every square matrix satisfies its characteristic equation. I think all of you know, if A is a square matrix, then determinant of A minus lambda is equal to 0 is its characteristic equation. Okay, so what Cayley-Hamilton theorem says is every square matrix satisfies its characteristic equation. Okay, now let us see what are the prerequisites to prove this theorem. Yeah, let us start with a 2 by 2 matrix. Okay, so first we see what is characteristic equation of 2 by 2 matrix. Okay, this is for example I have taken A is this. Okay, and characteristic equation is, we know, determinant of A minus lambda is equal to 0. That is what we got here. Okay, after simplification, what is the determinant of 2 by 2 matrix ABCD? So the determinant of 2 by 2 matrix ABCD is AD minus BC. So using that formula, you got this polynomial. So observe that if you have taken 2 by 2 matrix, you got a polynomial of degree 2 in lambda, right? And the same polynomial I have written like this. Okay, you please observe. So lambda square, okay, and lambda term and constant term. Okay, we'll come to this part later. Okay, let us observe the same thing for 3 by 3 matrix also. Okay, what is the characteristic equation of 3 by 3 matrix? Same formula. Okay, this is the determinant of A minus lambda is equal to 0, and you know how to calculate the determinant. So after calculating the determinant, what you got here is, okay, you pause the video and verify the calculations, that is up to you. But what you observe is the characteristic equation of 3 by 3 matrix is a polynomial of degree 3. That is more important. And you see the quotient, the leading quotient is minus 1. Earlier for 2 by 2 matrix, the leading quotient is plus 1. And here the leading quotient is minus 1. That is how, okay, when you write the quotients of the matrix, okay, we write like this. How we write? Minus 1 whole cube, because you got minus 1 as leading quotient for the 3 by 3 matrix, and here 1 as leading quotient for 2 by 2 matrix. Therefore I write it as minus 1 whole square. Okay, so minus 1 whole cube is minus, therefore take minus common. I got lambda cube minus 3 lambda square minus lambda 7 lambda minus 1 here, but minus 1 whole square is plus 1, so I got same quotients, that is lambda square minus 3 lambda minus 10 is equal to 0. Hope you understand this. Right, now the moral of the story is, if you take n by n matrix, then what happens? N by n matrix, the characteristic equation will be a polynomial equation of degree n. Okay, similar to 3 by 3, it is polynomial equation of third degree. It is for 2 by 2 matrix, it is a polynomial equation of 2 by 2. Now n by n matrix, it is a polynomial equation of nth degree, and the leading quotient will be minus 1 to the power of n, and you take it common, you will get some equation of this form. This is the first point, right? Now in the second part, we see what is adjoint of the matrix A minus lambda. Okay, again let us start with the 2 by 2 matrix. Okay, if you take A is 1 4 3 2 matrix, then A minus lambda is this matrix. It is not determinant, please remember. Now I want to find adjoint of this matrix. Okay, so what is adjoint? Transpose of cofactor matrix. So I calculated cofactors for each element. You know this, how you got this alternative plus minus, and what is the cofactor of 1 minus lambda? Plus. Okay, you remove this row and column, and you are left with 2 minus lambda. You got this. Similarly, you find cofactor for every element, and this is cofactor matrix, but adjoint is it's a transpose, right? So find the transpose, right? Now this is the transpose, therefore this is adjoint of A minus lambda I, okay, for a 2 by 2 matrix. And here what do you observe? See, observe that each element in this matrix is a polynomial in lambda and of degree less than or equal to 1. That means either it is a polynomial of degree 1 or less. That means constant can be treated as a polynomial of degree 0. Okay, that is the point. And then next point is, so how can you write this matrix? I write this matrix as lambda into something. So lambda into, what are the quotients of lambda here? -1, no lambda term, so 0. Here also no lambda, 0. And here the quotient is -1. Plus, and the remaining constants 2, -4, -3, 1. Okay, now if you add these two matrices, then you will get back to the original matrix, that is adjoint of A minus lambda. But what you observe is, see this is a polynomial, okay, in lambda, but it is a matrix polynomial because the quotients here are matrices B0, B1. I call this as B0 and this as B1, and they are 2 by 2 matrices. So hence this is a matrix polynomial, okay, in lambda. If it is 2 by 2, the leading power is lambda power 1. Now we will observe what happens to the 3 by 3 matrix. Okay. Now I start with a 3 by 3 example. I find A minus lambda I and I want to find adjoint. Adjoint means transpose of cofactor matrix. So first find cofactor matrix. Okay. So this, you know how you got this alternative plus minus. And to find the cofactor of 2 minus lambda, remove this row and column, and the remaining part you have 3 minus lambda, 3, 0, minus 2 minus lambda. That is how you form this determinant. Okay, similarly you find the determinant for minors for remaining elements. Okay, you know the basics of how to find a cofactor of a of each element. Now I found this cofactors. And then what happens? After finding cofactors and simplifying them, okay, you please observe, okay, actually this is cofactor matrix and you want adjoint, so I write transpose again. Okay, so by finding transpose, what do you get? Okay, again just you rearrange the things, first row as first column, second row as second column, third row as third column, and what you got is each element here again is a polynomial in lambda of degree 2 or less. Okay, at most 2 or less than or equal to 2. That is the main point. So again I write lambda square into lambda square quotient here 1, 0, 0 because there is no lambda square terms. Okay, similarly lambda into lambda quotients everywhere -1, 1, 2 like that, and constant terms. Okay, so altogether this is again put in the form of a matrix polynomial of the form lambda square, because we started with 3 by 3 matrix. We got lambda square B0 plus lambda B1 plus B2. What are B0, B1, B2? This is your B0, this is your B1, and this is your B2. Hope you understand. And each of them are 3 by 3 matrices. Okay, now the conclusion. So by seeing the examples of 2 by 2 and 3 by 3 matrix, my conclusion is, if you take a matrix, n-rowed square matrix, then each of the elements of adjoint of the matrix A minus lambda I, okay, I am not talking about matrix A, I am talking about adjoint of the matrix A minus lambda I, is a polynomial in lambda of degree at most, that means less than or equal to n minus 1. For 2 by 2 matrix you got lambda, okay. For 3 by 3 matrix you got lambda square. Similarly, for n by n matrix you will get lambda power n minus 1. Okay. Hence, adjoint A minus lambda I can be expressed as a matrix polynomial, okay, similar to this here or here, okay, matrix polynomial of degree n minus 1. Here you express this a matrix polynomial of degree 1. Here it is a matrix polynomial of degree 2. Similarly, n by n matrix, okay, if for n by n matrix, the adjoint of A minus lambda I can be expressed as a matrix polynomial of degree n minus 1. Are you convinced with this? Otherwise, you please pause here, okay, go back again with the examples of 2 by 2 and 3 by 3 and try to convince with this two conclusions, right? We will go to the next point. Yes, finally, I want to show you some properties of square matrix which we will use it in the proof of Cayley-Hamilton theorem. Okay, suppose A is any square matrix and dat A not equal to 0, we can find its inverse, that is A inverse is the form, how do you find A inverse? It is 1 by dat A into adjoint A. Please understand that A is a matrix, A inverse is also a matrix. Adjoint of A is also a matrix, but dat A is a number. So you are multiplying a number and a matrix. The result is also a matrix. Okay. Now, you can multiply both sides with dat A because dat A is not equal to 0, and you got this equation. And then I multiply this equation both sides. This is pre-multiply. Pre-multiply means multiply, okay, front, okay, with A. A is a matrix and here dat A is a number. Therefore, I can directly multiply A inverse with this A. Similarly, here A dot adjoint A. Please understand that adjoint A is again a matrix. So, just what I did is, I pre-multiply the above equation with the matrix A. And you know that A dot A inverse is I. Okay. So, identity matrix is equal to the right hand side is as it is. So, this is true with any matrix A. Of course, even if the dat A is not equal to 0, this is true. Okay, the yellow, the shaded part in yellow is true. Okay, for singular matrices also. Now, let us replace A. This is true for any square matrix. Suppose I replace that with A minus lambda I. So, A minus lambda I is also a matrix. Okay, it is a square matrix. So, just replace A by A minus lambda I. Got determinant of A minus lambda I into I is equal to, in place of A, I got A minus lambda I into adjoint of A minus lambda I. Please remember that dat A minus lambda is a number multiplied by I is a matrix. So, this is a matrix again. Similarly, A minus lambda I is a matrix. Adjoint of A minus lambda I is also a matrix. Okay. So, we will use this equation in proving Cayley-Hamilton theorem. These are the fundamentals of Cayley-Hamilton theorem. You please recollect once before going to the proof of Cayley-Hamilton theorem. Thank you.